Okay, so let's get started. So today is a little bit special. So there is no project update, about several talks, starting from me with overview, and then Lei and Ben are going to give a talk respectively over the project they have already accomplished, most part of it, and Shita is going to give a talk about a new project that he just started, and then just a bit of overview of what I have been doing, and a little bit of introduction myself that I got an undergraduate from China University Geosciences Beijing. Actually, I'm currently in a hotel in my undergraduate university, and then got my master's in China's Academy of Sciences before I moved to University of Minnesota for a PhD, and then a postdoc at the Scripps Institution of Oceanography at UC San Diego. And having worked with Zhang, who was at Chinese Academy of Sciences as master's, and then with Mark Hirschman for my PhD at University of Minnesota, and also David Koshlet was my PhD committee chair, and also partly because of him that I moved to Scripps for my postdoc. And although none of them are doing information science technology, but I think the way that I think about science that helped me to construct the way that we solve these problems. So the question that I am interested in, let me see, how could I move forward? See next page. Okay. So the general question I'm interested in is carbon cycle in the Earth system. So why we care about carbon? First of all, carbon is life essential elements. Actually, we're all made of carbon. Without the carbon, there is no life on this planet, or the life that we know, defined as carbon life. And also, carbon is very crucial for the habitability of planets. And also in the Earth's interior, carbon is a crucial element to keep the interior of the Earth moving. And give you some more detailed examples relevant to the carbon or life that in the 1920s, and both Zhou State University and Cambridge independently by pairing and the Heterogeneity hypothesis. So they have the idea that inorganic life, that inorganic compounds that evolve into the organic compounds, and then with early evolution of life. And of course, similarly, Goldschmidt, etc., that in early days at I think it's Norway and in Germany, back then that developed the idea that some elements are life essential. So I categorize elements, including carbon, as the life elements. And then at 1953, by the well-known Miller-Urey experiment, where they simulated early Earth atmosphere and then created a sparkling as a semi-lightning early Earth, and then created organic compounds. So carbon is crucial for us to understand the beginning origin of life as well as the evolution of life by itself. But not only that, carbon is also crucial for the environment that the life is in. For example, early in the days at the Scripps Institution of Oceanography, UC San Diego, Keeling, so he kept on observing the carbon dioxide concentration in the Earth's atmosphere, and beginning at the Manoa, Hawaii Observatory. And since then, we have known that the carbon dioxide concentration increases with time in the recent, at least a couple of decades, and then drive the question of global warming as well as climate change with the particular attention that everyone that with decent science background would know that is a very important question. Also, carbon is very crucial for a habitable planet. For example, one of the well-known story in the geology is a snowball Earth. That is, the glaciers at both polars has been extended so much that to the equator zone, so that the entire Earth was covered by snow. By the end of a snowball Earth, in the geologic history, ended with a carbon dioxide produced by volcanic activity, and therefore the carbon dioxide concentration in the Earth's atmosphere, or the greenhouse concentration, are several orders of magnitude higher than our current Earth atmosphere, and therefore they thaw the snow starting from the equator and end the snowball Earth. So, of course, carbon dioxide is also very important for the water on Mars, like goolies that people find in around 2000. And there was water flowing on Mars before, but currently, if you put one bottle of water that you are drinking on Mars, the water won't be stable. That is purely phase diagrams, as we could see. And one of the crucial things that pure water is not stable on Mars now, but was stable before, was that there was the greenhouse effect. And in particular, carbon dioxide played a significant role in the early evolution history, geologic evolution history of the Mars. But of course, we know now that Mars has the water that's not a pure water, but with a very high salient concentrations that led it to be stable beyond the pure water stability zone. And here, in the recent couple of years, I'm interested in working on the role of carbon, on the role of working mechanism in the Earth interior. Here I give you an example of why carbon is very important for us to understand the Earth interior. And there's a classic example of the carbonatite melting work that people have done before at the University of Minnesota, of showing by only have a very small amount of carbon in the Earth at the mantle that could explain the low seismic velocity all the way beneath 300 kilometers beneath the mid-ocean region basalt, and also explain high conductivity and as well as various geochemical phenomena. So very small amount of carbon in Earth interior is important. So that's one of the whole picture of why carbon is very important. And here in the recent year, I'm focusing more attention on that very last one. But before we look at how carbon is stored and distributed and cycling in the Earth interior, but we first have to look at how carbon is stored, or what's the interior composition structure of the Earth. And here in this figure, it shows the different mineral abundances in Earth interior. Here, the horizontal axis, if you look at the lower one, that is a volume ratio. That is, if the volume ratio is 1, that means it's composed of everything. So the vertical axis is increase of depth, and on the left, and on the right side is also increase of depth. If we calculate the interior of depth in considering Earth density, and that is equivalent to pressure. So 1 gigapascal corresponds to approximately 30 kilometers of the rock depth in the Earth's interior. And then we could see that in the Earth's upper mantle, we mainly have the olivine garnet pyroxenes, and then with increased depth at about 410 kilometers, there's a transition of the olivine crystal structure from olivine to wastite, and then at 550 from wastite to rigidite, and then to lower mantle transformed to bitumenite. And this is consistent with the observation that the seismologist has to see. So if you see the upper x-axis in the upper end, you will see the densities that with the increase of depth, the Earth's density gradually increases. So this mainly comes from the evidence of seismology. So this picture is very crucial because for us to understand the carbon storage distribution and cycle in the Earth interior, it all depends on the major ones, major minerals here. Here I will show another figure of flow of the ideas, of how people have this idea that the Earth's interior structure or minerals looks like this. This did come from scratch. So let's turn the clock 100 years ago. So at the very early 20th century, people began to have collect seismic waves and therefore analyze the Earth's interior structure. So Croatian seismologist Mohovic, and he identified there is a seismic discontinuity, which nowadays we define as Earth's crust at 8 kilometers beneath the oceans and about approximately 30 kilometers on the different continents. Later on, another German seismologist, Gutenberg, identified that with depth 2,900 kilometers, another seismic discontinuity. Actually, that is Earth's metallic molten core and the Earth's solid silicon mantle boundary layer. So people identified it a long time ago, but people were not clear what was exactly inside the Earth. And this have to combine with other progress that science has been made, starting from Bragg diffraction that began to allow us to understand the crystal structures, and then the well-known Bowen reaction series. For most of geologists in Geology 101, people will know that the mineral crystallization during the basalt cooling process. So his early days of work showing that using laboratory controlled experiments, so we could analyze the relationship of different minerals with each other and together as a function of temperature and pressure. And also, in early days, in 1930s, seismologists already identified these seismic discontinuities in the Earth's silicon mantle, and so that's the detailed structure of the Earth's core, that we have a solid inner core, which is mainly made of iron and nickel alloy, and an outer liquid core that's mainly made of liquid iron with some light elements. And later on, people began to understand more and more of the crystal structures using the Bragg equation. We're using the X-ray diffraction patterns to understand that. Well-known one is by the Harvard University professor Percy Bridgman, and he squeezed all kinds of minerals or powders and at a high pressure and analyze that crystal structure. And then he won the Nobel Prize in physics because of that. And later on, different labs were competing for who could be the first lab to create the first man-made diamond. And people already know that the graphite and diamond transition occurred at a relatively high pressure. This could be calculated through thermodynamics. But people were competing with each other to see who could be the first lab to reach such high pressure in the laboratory conditions. And then GE Laboratory won the competition, and they won the race, including in the race together with the Harvard University Percy Bridgman. So they won. GE Laboratory, the first one, made a man-made diamond, and at this Precambrian period, a guy from Melbourne University, later on Australian National University, Ted Ringwood, and made the first discovery of olivine to Wasiite transition at 14 gigapascals. And this transition successfully explained the seismic discontinuity at about 410 kilometers that identified more than 20 years ago. Of course, later on at the Scripps Institution of Oceanography, UC San Diego, Dan Mackenzie and Bob Parker, two British guys and they first proposed the plate tectonic theory in a publication written in English. And then as time moved on, Dave Mao and Bell, Mao is well known as a scientist at the Carnegie Institution. Actually, Carnegie is in Beijing now, working at Beijing now after retired from Carnegie a year and a half ago. And then they reached 100 gigapascal, very, very high pressure in laboratory conditions. And this allows people to do a lot of research close to the Earth's core mantle boundary conditions. Now the world record is almost 1,000 GPa nowadays, the diamond emerald cell. And then in 1980s, seismologists that globally has already synthesized a database that could get average density and the velocity of the Earth interior, and then we know more details, and then more discontinuity were confirmed by analyzing the data in more detail, such as Peter Sherry's work at the Scripps Institution of Oceanography. And then 1995, this is a classic, like a summarized paper by review the composition of the Earth. And then what happened in the 20th century, people, of course, we know the general interior structure and the composition and mineralogy of Earth interior, but people are not so sure about some more details. And for example, one of the most heated debate in the Earth's lower mantle, Earth's mantle structure is the abnormal structures. People call it the large low shear velocity provinces, we'll call the LLSVPs. One here, the other one here, or above Earth's core mantle boundary here. And then one locates beneath the Pacific, the other beneath the African. And here showing this seismic tomography of the red two piles. So they are very special for both seismology, geodynamics, and geochemistry reasons. So that's the general idea of how people come to this figure of saying, okay, most of Earth's mantle is made of silicon minerals. Well, it depends on what kind of specific minerals that they are. And there are certain anomalies. Here, we only give you the average, but there are anomalies, heterogeneities in Earth's mantle. So where's carbon? So there are very, very few amount of carbon, and there are very, very few amount of hydrogen in Earth's interior, which we say they are in the order of several ppm to hundreds of ppm. So 1 ppm is 1 parts per million, or 10 to the order of -6, which is extremely small. But they're all important because most of the hydrogen, or you could say water, equivalent in terms of element mass, locates in the Earth's interior, and similarly for Earth's carbon. And different than hydrogen, which likes to locate in the vacancy in the Earth's silicon minerals like olivine, wastite, and ringotite, carbon doesn't have a position in the silicon minerals. At least that's the mainstream idea, at least in the Earth's upper mantle transition zone. And the carbon have to stay by itself as other independent minerals. For example, as carbon, the carbonatite, or you can see as like say Mg or magnesium carbonate, or as a calcium carbonate, or even some sodium carbonate, and the war as elemental carbon, such as graphite diamond, or some more reduced form of carbon, that the condition could be so reduced that iron metal could exist, and the carbon could react to form different kinds of metallic compounds. So that depends on the metal carbon phase diagram in Earth's interior conditions. So therefore, if you relook at this figure again, you could imagine that carbonate is like carbon dioxide plus some oxide. And then this elemental carbon, so this is CO2, this is elemental carbon, is something that more reduced than elemental carbon. And therefore, the storage of Earth's carbon in the Earth's interior is dependent on the mantle oxygen fugacity. And of course, the Earth's mantle oxygen fugacity is not homogeneous, and that causes the heterogeneous distribution of Earth's carbon in Earth's mantle. And later on, Lei and Ben are going to give a talk respectively talking about diamond heterogeneity as well as carbonate heterogeneity in the Earth's mantle. And of course, we're not only interested in the storage as well as the distribution of carbon, but are also interested in the cycling of carbon between these reservoirs. For example, a lot of work has estimated how much carbon has been pulled from Earth's surface to the Earth's interior, as well as the other way around. And furthermore, the Earth's carbon also cycles within the Earth's interior in the different forms, as from carbonate to diamond to more reduced form of the metallic size. And Earth's oxygen fugacity, which is a crucial part that controls the carbon stability. And not only has a wide heterogeneity within between the different places or between 2Ds, but also has such a contrast with increase of depth. And therefore, there's a large 3D oxygen fugacity cause a large 3D heterogeneity in terms of carbon storage and distribution in Earth's interior. So that is one of the topics that have been mainly focused on in the recent year, to look at what's the role carbon plays in the working mechanism of Earth's interior. And then we'll move to the carbon cycle between Earth's interior and exosphere. And Shichao is going to give example. We're not talking about the hydrogen gas, but it's something that fits well on the general interest that I'm moving to, is to look at the carbon interaction between surface and between Earth's surface and interior. And finally, I will move to carbon and life in the future. So why? So just now I was mainly talking about geoscience. So that's why we're curious about the carbon. What's the general big question in terms of carbon? And next I'm going to talk about the why information science. So in geology or geophysics or earth science in general, normally people have a theory and then people go to the field to test their hypothesis, to test it's wrong or right. That's okay. And then later, when time goes by, people began to have more and more quantitative observations. For example, we squeeze a rock and analyze all the element concentration as well as isotopic compositions, since the analytical chemistry developed quite fast. And we can also deploy all kinds of seismometers or different equipment that could analyze the geomagnetic or electric conductivity data in the Earth. And later on, people began to move on the simulation experiments, whether you can do in the laboratory or you can do on a computer. So all this greatly improve our understanding of the Earth's composition, evolution, structure, both from the reverse method as well as the forward modeling method. But nowadays, the data is so abundant in both natural observation and the experiment or the simulation experiments, then we have to introduce the information science technology to do it. So that's the reason why is a crucial need for, at least for earth sciences to do so. Actually, this is not only a question for earth sciences, but also similar in other fields such as the medical sciences, pharmacy, or biological science, for example, as well as social sciences. So there's a wide implication for information science technology apply in those fields because data is too much. So here are some of the examples. In the recent years, people take advantage of information science technology to revisit their earth science questions. For example, this is a talk D. Kim gave in our seminar. Actually, some of you probably have attended this seminar. I think his video is still on the link that you could watch on YouTube. And he used the unsupervised learning to look at the different seismographs and then look at the Earth's core mantle boundary low velocity zones. Another example was a paper that I read in my group reading a couple of weeks ago and talking about their paleontology. They're talking about different fossils. And then they use the big data and the supercomputing to reanalyze this data and get a very different understanding. And both of the work were published in Science this year. And of course, another big program is called Deep Time Digital Earth, and they try to incorporate all the data relevant to the Earth online on the big same platform, and that could be shared by scientists from around the world to do data mining to reach their own scientific goals. And here in our program, which we apply Python due to internet worms, we use both Python R to do different types of algorithms, and then we use the cloud computation to realize a lot of our ideas. So this week, later on, Lei, Ben, and Shicha are going to give some science examples or update. And then next week, we will hear 3 different very short introductions from the internet worm group, cloud group, as well as a machine learning group, to tell us a little bit about some basic mechanisms and the overview of the working structure that they have had. So with that, that's the end of my talk. I think that's so much about it. So if you have any questions for an audience, I could give a quick answer now, I suppose. And if not, I'm going to stop sharing, and then Lei could share her slide.